Next, we want to talk about bonds. Actually, we already did. Remember, bonds join atoms together, and this is from the gaining or losing or sharing of electrons, those valence electrons, the outermost ones, to fill up the outermost shell, whether that means their current valence shell or the previous one. We already talked about ionic bonds. We're talking about ions, and they become like magnets where you have oppositely charges, so sort of like north and south, but plus and minus, and opposites attract. So they will form these bonds. Now these are weak bonds, like sodium chloride, table salt. The crystals in salt are actually weak bonds, and you can prove this two different ways. One is if you have a salt shaker that's stopped up, how do you unplug it? You can take your thumb and crush the salt. So that means it's weak enough that you can break it up. It's like pulling magnets apart. Second one, just run water over it. Salt dissolves in water, and we'll talk about why it does that. But it does that, and so it's quite weak. Now, covalent bonds, though, are strong. These are ones like made out of your tabletop is made out of. So you can't really crush your desk with your thumb, and if you spill water, you don't have to worry about it dissolving away. Covalent, co meaning with, this is the sharing of the valence electrons. And as we talked about before, we talk about sharing. There's different ways we can share, and you can share nicely or not so nice. Now we tell our kids to share nicely, and that will form non-polar covalent bonds. So here we have two little kids, like 5 years old. They go down to the playground, and each one has one car with them. And they do what their parents told them to do, which is share nicely. So they start to play together. And they start zipping the cars back and forth to one another. And in this configuration, you ask one kid, how many cars are you playing with? And he'll say 2. And you ask the other kid, how many cars are you playing with? And he'll say 2. Yet there are only 2 cars. Here we have hydrogen, each with 1 proton, 1 electron. It wants to have 2 in its outermost shell. And what they'll do, since neither one of them is stronger to take away from the other one, they will just share. And with these electrons zipping across nearly the speed of light, it gives each one the appearance that has 2 electrons in both their outer shells. So they are content. This is hydrogen gas. Since they share evenly, there's no poles. We can also do this with something more complex. Now here we have carbon. Remember, carbon atomic number of 6. 6 protons. Rule of thumb, 6 neutrons, and it works. And 6 electrons, 2 in the first shell, and remember 4 in the outer shell. We need 4 more electrons in the outermost shell. And we can get that actually by adding in 4 hydrogens. Now if we follow, they made on this animation the hydrogens a little bit smaller so you can follow them. It goes 1 time around the carbon, 1 time around the hydrogen. The one from the carbon goes 1 time around the carbon, 1 time around the hydrogen. So giving the appearance that hydrogen has 2 now, and the carbon has another 1. And we add in the other 3. Carbon fills up its outermost shell, and each of the hydrogens does as well. And neither one of them strong enough to pull it away from the other one, so again, non-polar, even sharing. This is a non-polar covalent bond. Now we can represent those pairs of shared electrons, a little stick figure here. And so there's one between this carbon and this hydrogen, and this hydrogen, this hydrogen, this hydrogen. And of course we give them names. This is methane. Now, of course, if we have kids that play nice, we have kids that don't play nice. Always reminds me of my brothers. They're a lot older and bigger than me. In this case, we'll have one of the 2 bad boys of the periodic table. Oxygen or nitrogen. Here we have oxygen atomic number of 8. 8 protons, rule of thumb, 8 neutrons, and it works. 2 and then 6. It needs 2 more electrons to fill out that outermost shell. And again, we can get that from hydrogen. Now, from 2 hydrogens. Now, this animation, they never got to work right. Okay, the electron should go one time around the hydrogen and then 2 or 3 times around the oxygen. It does really just the opposite. Because with the configuration of the protons in here, there's 8 pulling on this side and only 1 on this side. The shells, the orbits for oxygen are actually collapsed. So it can pull more with those 8 protons. And not enough to rip it away from hydrogen, to rip that electron away, but enough that it unequally shares. It spends most of its time around here. Because at times, like right now, that proton's exposed. And being exposed, there's a flash of positive charge. And then when there's electron back, neutral. So it doesn't form a fully positive charge, but what we call a partial positive charge. And of course the other one will do this as well. So it'll be a partial positive down here, and where that electron spends most of its time in the shell on the opposite side, there will be a partial negative charge, and hence the polarity of this bond. Down below we see the stick figure structure. Of course this is H2O, this is water. Partial positive one end of the molecule and partial negative at the other end gives it the polarity, and also leads to the very unique characteristics of water. Since each one of these has this partial charge on it, like we talked about charges, opposites attract, partial opposites also attract. And we call these hydrogen bonds, because one thing that it has in common is hydrogen's being taken advantage of. Okay, other elements like chlorine and such, fluorine, can rip the electron away from hydrogen. Other ones share nicely. Oxygen and nitrogen are the two that will not share nicely, hence forming these poles, these polar covalent charges and bonds, and also now they will attract one another. And because of that, water has an extra high density. Again, giving water a unique characteristic. Because of these charges, it will attract other molecules that have these polar covalent charges, the bonds. The more that they have, the more they bond to water. Okay, they act like little life preservers, little floaties. And the more of those floaties you have on a molecule, the more it will suspend in water. So why we call water a universal solvent. Also, anything that has ionic charges, we said before, like table salt, sodium chloride, it also readily dissolves in water because partial charges attract full charges. Why we call this a universal solvent? Because most, now goes beyond, most things do attract and dissolve in water. Now there is a handful of molecules in the universe that don't, and of course oil and water don't mix. The ones we mentioned before are nonpolar covalent bonds. They don't. And that's because there's nothing for the water to hold on to help dissolve it. The H2, there's no charges or partial charges. The methane, CH4, no charges or partial charges. So they do not dissolve. You put that into water, it just bubbles through. Also with this density, it makes water very dense. It also makes it have a high boiling point. And it's like pulling one magnet out of a box of other ones. They all stick together. You can separate them, but it's going to take you more energy. So water has a very high boiling point. Also, when it does freeze, it actually, to go into a crystalline lattice, has to expand. And that's why ice floats. It's less dense than water. And at room temperature, where other molecules similar to this, like hydrogen sulfide, H2S, is a gas. 100% of it will be a gas. Water is usually in a liquid form. And so it's also a great coolant. So many different things. It sticks to surfaces. It adheres to each other. What we call adhesion and cohesion. That it will actually defy gravity and form a water droplet, a dome structure, because it attracts to itself. And it sticks to things. Think of your car. When you wash your car, you have all those water droplets all over it. So anytime you see an OH or an NH bond, this will form a polar covalent bond, and this will help to attract to water, especially, or each other. Other partial bonds, partial charges, and also full charges. Those things that do dissolve in water we call hydrophilic because they're water loving. Literally, that's what it translates to. And if it doesn't, like oil, we call that hydrophobic because it's water hating or water fearing. It repels water. So far we've seen a number of bonds. We've only looked at single bonds, that little line between atoms. A double bond is when two atoms share two pairs of shared electrons. It looks like an equal sign between the two atoms. And a triple bond looks like a funny equal sign, 3 dashes in between two atoms. They're sharing 3 pairs shared electrons. We also have a rule: to fill the outermost shell, hydrogen wants 1 covalent bond, oxygen a total of 2, whether 2 singles or a double. Nitrogen wants a total of 3, so 3 singles, double and a single or a triple, and carbon just needs a total of 4. And we've already looked at some examples. And the animations, even though they don't have sound and closed captioning yet, they are available online in Canvas in order for you to review. Now, formulas, molecular formulas show us the ratio of atoms that are used to put together the molecules, such as C2H6O means we have 2 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen in order to configure into one molecule. Now, so far they've been very easy or simple examples we've looked at: H2O, CH4, ones that we haven't had much of a problem with. We don't have to get very large though. One like this with only 9 atoms in it, that actually you can reconfigure it into different structures. When making structural formulas, it shows you pretty much exactly what it looks like. Getting those stick figure structures connecting the atoms, showing you where the covalent bonds are between the atoms. This one has 2 carbons, 6 hydrogens, 1 oxygen. Each of the hydrogens only has 1 bond. Oxygen has a total of 2, and each of the carbons has a total of 4. So this is a configuration. Commonly this is referred to as ethanol. The one down below, it also meets the same constraints. 2 carbons, 6 hydrogens, 1 oxygen. Each of the hydrogens only has 1 bond, oxygen a total of 2, and each of the carbons a total of 4. However, this does not look like this up above. The one above is ethanol. You might call it alcohol. You drink a little bit of this in a beer, like 5% is alcohol, 10% of wine, or a higher percentage in other alcohols or liquors. Down below, this is called dimethyl ether. Putting the oxygen in the middle makes this an ether, and actually this above will give you a little buzz if you're of age. The one down below will kill you if you drink enough of it. Well, the one up above will kill you if you drink enough of it, but you have to drink a heck of a lot. Ethanol is actually the second most abundant liquid that we can drink on this planet. The one down below, not so much. You take a shot of this, you'll at least go blind or probably die. Okay, so remember the difference in structure and different in function. Okay, slight difference in structure, big difference in function. This one kills you. These are called isomers. Remember that prefix iso means the same. These have the same molecular formulas but different structures. Why? When you go in the lab and the only thing you see is this labeled C2H6O, you have to be careful because which of the different types is it? That's why stick figures are more specific, but of course that's why we give these names like ethanol and dimethyl ether. Different types of reactions we see. We see synthesis reactions. These help to build things up. A plus B gives you now AB. We've joined 2 particles together to make them bigger. Decomposition, just the opposite. Take some large particle and you break it up into its constituents. AB equals A plus B. Exchange reaction. I always like this one. Molecule rearranges, and gain or lose just switches. AB and CD now AD and CB. Always reminds me of my brother's senior prom. Everybody went with one date, left with somebody else. Some couples that were dating for 3 years had arguments and split up. The only one that came away with their original date was my brother with his date, to which he later married, the witch. I'm not a hater, she started it. Now here though, reversible, most Okay, highlight, underline, circle, whatever in your notes. Most chemical reactions are reversible. That synthesis you build up, and at times you need to tear it down, and you go back and forth between the two. What's very important are ones that are not reversible, because what are you going to do then? Usually they become waste, and you get rid of them.